EEE145, Chapter 8, Generator Protections. So here we're going to ask ourselves, for introduction to definitions, what are the two categories of generations we typically see in the power system? So we're going to typically have a large scale called bulk power generation. This is the big generators, the nuclear plants, fossil plants, hydro plants, this type of stuff, right? They're about typically 20 MVA and more. Then you have the smaller ones. These are called distributed generators. This is typically your renewable energy sources, maybe some very small gas turbine plants, and other like unique ones like biomass or fuel cell, this type of stuff, right? Full power generation, typically the big one we're going to see. So most generators in the power system work type bulk power generators, bulk power gens. Typically, this is going to be your large hydro plants, your fossil fuel plants, nuclear plants. Those are your big three you're going to see. Good note, in fossil can be both gas and coal. You technically have oil, but you don't use that too much. Okay, what about renewable energy sources? Or whether they consider, again, distributed generation. For the longest time, we didn't really pay much attention to it, but it's getting pretty big, especially in California, that you're gonna have larger scale ones. So we kind of made its own category for generation, right? So you have like a specific hydro category, solar category, and pretty much everything else. Okay. So remember, we're trying to protect these generators. So the question would be, what are the problems, right? You have to understand your system and understand the problems before you can start coming up with solutions. So internal to the generator, the two major problems you'll see are stator faults, which is basically the winding damage that will occur. And then you won't be able to create that electric field anymore, and then your generators will just not work. Then you have the other main field called rotor faults. Again, this is more winding damage. And this is a big deal because once you start having winding damage, you're going to have to start replacing things. So that's internal to the generator itself. Outside, you still have fault currents that need to be detected, but they can be on the outside of generators. You get excitation issues. So trying to create that magnetic field, that whole circuitry has some problems sometimes. You can have unbalanced current. That could cause an issue in the generator because it starts vibrating. You can also have saturation, where you're saturating the magnetic field and you're not going to be able to produce the correct amount of energy. Mechanically, the big things we're going to we have to watch out for is overheating, because any mechanical system that moves will generate some level of heat. So we want to make sure we're not overheating the generator too much, because then we're going to start burning things up. Other big thing is called loss of synchronism. So remember, the whole system runs on 60 Hertz. So synchronism. So the whole system runs in 60 Hertz. So the generator is connected to the system. So the generator must run 60 Hertz. If it stops running at 60 Hertz, it speeds up or slows down. That's called we're losing synchronization with the system. Okay, and that's really bad. So all these have issues, and we need to have ways to protect all these problems. Now, those are the problems with generators in general. In the power system, there's two major types of generation setup. You have directly connected generators. These are typically your smaller generators, your distributed generations, so smaller generators. Notice that direct connected means there's no step-up transformer. So that's the direct connected. So whatever the voltage is on the system, that's the voltage the generator is running at as well. The more popular one you're going to see are the unit connected generators. These are your bigger ones. Your bulk electric generators are going to be unit connected. So you're going to have a GSU attached, which is a generator step up transformer. Okay, so they're called GSUs. Right, that steps up the voltage from the lower voltage of the generator to the higher voltage of the power systems. Again, majority of the generators in the United States are unit connected. So majority in USA. Okay, because in the United States, we have a big grid. We go for economy of scales where we try to typically build the biggest generators possible because they're more efficient. So we have these big giant transformers unit connected to the grid. Okay. So the main thing we're going to talk about this session is going to be protecting the generators from the electrical faults. All right. So here, let's do a brief overview before getting into that detail. We have what are the protective devices we typically see for directly connected generators. The biggest one, the most important one, is your 87 generator differential. All right. That's this one right here. Other important ones we're going to see is a 51G. So you typically want some ground protection. So you have ground time over current, TOC. You typically see some voltages. You want to make sure your generator runs in the correct voltage level. So 2759, this is over and under voltages for small generators. And then you'll have a 24 relay, which is a volts per hertz, which we'll talk about that soon, probably next class period. So these are like the basics protection level you're going to see for any type of generator. There's more than that, but these are like the basic things we really should have to cover. Okay. I guess we could call it the extra ones you'll see here. You got a 46. This is your negative sequence relay. Another 51V, this is your time over current relay that's voltage controlled. The 32 is a prime mover relay, which we'll talk about these later. 40 is your loss of excitation. So as you can see, there's quite a lot of protection wrapping around a generator, and this is even a directly connected one, because there's a lot of money at stakes here, and generators are very complicated devices that could get damaged very easily, so we need to make sure we have a lot of protection around these things. Typically, generators are probably the absolute most expensive unit on the system, and you want to protect them the most. So here's probably the bigger, more common one is your unit connected generator. So unit generator diagram here. These are the protected devices. So in addition to everything we talked about previously, we're adding some more. So we have let me use a different color. We have a 59G. And that is, let's get the markers out. Right here, 59G. That is a over voltage, a ground over voltage. So that kind of checks the ground circuit. We have our 87 differential for the generator specifically. So it's an A7G, your generator differential. Sometimes we short it to diff. And that is, let's get the colors out. That's this one right here. Okay. Next, we have a second layer of differential, because we remember we like backups. We like something super expensive. We want to have multiple layers of protections. So we're at A7TG. This is the GSU transformer plus the generator itself. And this is called a combo differential. Okay. And let's write that in. That's this one right here. Okay. And then third, we have if you see down here, we have a unit service bus. So this is called the auxiliary bus. So we need another A7 differential for the unit auxiliary transformer, UAT, unit auxiliary transformer. Okay, so we have a kind of smaller transformer right here, and we have a differential there to protect it. Okay, some people might ask, well, what does this auxiliary transformer feed? It feeds a service bus, which typically is like your lighting, your the relays might be fed off of this, your excitation circuits fed off of this service bus, fans, water pumps, anything to any electrical power needed to support the whole generator is fed off this unit service bus. Okay. So the main thing is you see there's 3 A7 relays sets here, a generator one, a transformer generator combo one, and then a unit auxiliary transformer. Okay, so pretty much exclusively for today, I want to talk about differential protection for the generators because it's so important. So here you have a very small generators. Small generators don't cost that much, so it's not worth it to get a true 87 differential because they're quite expensive. We could cheap out and get a 50 overcurrent relay. So we could make a quote unquote differential by looping both terminals, basically the positive and negative terminals of a phase from the generator. Okay. So what this means is you have a phase right here. You have current flowing out of the generator, like so. And for current to flow out the positive terminal, it must flow out the negative terminal. And so you can reroute it all the way here. This is your neutral point right here. You'll have current coming up to neutral this way. So if you could wrap your CT around 2 loops of wire, you could get all the current coming out the generator and all the current going in. So the I out plus I in should equal a net flux of 0 in the CT. So basically is you're wrapping the input and the output of the generator wires, and then that should always net a 0. So here's a phase, that's the current going out. And then you also have the current coming back in on a phase as well, right here. Okay. And both of those should equal up to 0. Okay. And so again, this is how we get a cheap 50 relay to act like a makeshift differential. How can you increase the sensitivity to differential protection? You can make you increase or decrease the 50 pickup, right? Because that's the amount of current we'll need to trip. In essence, this is your I delta that you're trying to change. Okay. So again, it's just a very cheap version to do it. I honestly haven't seen these too often or pretty much ever in the system, but I'm sure there's some places that wanted to cheap out, right? Now let's go on to the more bigger standard one you're going to see. Is you'll see a large generator. You see you have 3 windings. Again, on A phase, you always have your positive terminal generator and negative terminal generator. So remember, for any generator, you have 6 wires. You always have A, B, C positive going out, typically capital letters. And then the negative terminal coming back in is it's like that. Okay, so you have always 6 wires. So for A phase, you have the main wire, the actual wire itself going through the transformer. I mean the generator. This is where the current conducts. Now we could see that we have a CT coming out through here. And that CT is reading the negative terminal of generator and is going to an operating coil right here. On the other side, you can see the current going out the generator is going through a CT right here. And that CT current is flowing into the I operating coil of the differential right here. And then these loop back into the CT circuit. So you can see we have a differential at 87 G for A phase right here. Now, some suggestions whenever we're setting up this differential for the generator. CT ratio should be the same because there's no voltage change across the generator. So the current going in has to equal to current going out. So the CT should be exactly the same. When I say exactly the same, I mean they should be the same ratio, the same burden. Really, they should be the same manufacturer and built from the same assembly plant on the same assembly line. The typical, we try and make them called sister CTs. Okay, you really want them to come from the same place. That way there's no metal, there's no variation in metal density or workmanship. Okay, because you need these as accurate as possible to be perfect copies of each other. The CT secondary circuit should be exclusively used for the differential relay, so don't jam a bunch of other relays on this. You only want it for the differential. The relays should be the same make and model. This is an old mechanical relay. You need one per phase, so you need to make sure they're exactly the same model. You can't mix and match them. For the differential settings, you want the 87 pickup to be as low as possible so it trips off of anything, because the current should never ever be different in this generator. If it's ever different going in versus what's coming out, you have some problems. We should never wait as and trip as fast as physically possible. Now, no time added, plus we also have the CB time because it takes time for the CB to operate. This should all be roughly, well, hold on. Let me take that back. No time delay added. I would say mechanical relays, we try to go as fast as possible, but there'll still be some delays. We try to say roughly 20 milliseconds is the worst case scenario. Modern microprocessor relays, can be faster than 20 milliseconds, but a good rule of thumb is one cycle, which is 16.67 milliseconds, or 20 milliseconds is the fastest that the relay can operate. Okay, so anytime you're looking at about what is no time delay added, just remember the relay needs at least one cycle to process, or 20 milliseconds. But even still, 20 milliseconds is very fast in terms of protection. Okay, so there's no difference in the differential itself from what you learned in the previous chapters. Current going in has equal current going out. We could figure out fault current, and we could do some calculations. So here, this is where we typically take our 15-20 minute break. I have a differential protection problem set up. So why don't we go ahead and work on this? So just to give you an idea, we have a generator with an A7G relay attached to it. The pickup for this relay is 0.5 amps. The CTs are 1,005 on both ends. While the generator is getting online, we have an internal fault within the generator. So right inside the generator, right here, where F is, you have a fault before we're connected to the grid. So calculated three-phase fault current coming out of the generator. Okay. So the generator is going to be producing some amount of fault current coming out. Okay. And so, for example, if you have a fault here to ground, it's going to loop out back this way. So this is the path of your fault current. It's going to go through here. Okay. And so you're going to have fault current flowing to one side of CT and none on the other. So this should have 0 amps flowing through because we're not connected to the grid yet. The other side will have something flowing here, and you have to figure out what this is. That's what I want you to do. So calculate three-phase fault coming out of the generator. And then let's go ahead and check what each CT is seeing. So figure out how much CT fault current is flowing through one side and the other. Find your how much current is going through the operating coil of the 87G. So find that delta I and ask, will it generate trip offline because we have high current, and how much exactly and how much current is there exactly compared to your pickup, see if it trips or not. Okay, so we'll be back in 15-20 minutes to check your answer. So a little bit of calculations, get your calculators out, see if you remember how to do some fault current calculations and see some differential calculations. Okay, see you in a little bit. All right, welcome back. So here we're gonna go over differential protection for this generator setup. So remember, first thing I asked is let's calculate the three-phase fault current coming out of the generator. So remember, we have fault current. We assume that we have 1.0 per unit voltage because the generator is online and ready to get connected. And the only thing stopping this fault impedance from going to infinite current is the impedance of the generator itself, which is our XD double prime. So we're gonna have I equals V over fault impedance. So here we have 1.0 per unit voltage divided by XD double prime, which is 0.1 per unit ohm. So we have 10 per unit amps, all right? And so our base value or the base current for our generator is going to be 20 MVA divided by square root of 3 times 13.8 kV, because that's what the generator, that's the MVA of the generator and terminal voltage of the generator that was built. That's 837 amps is our base. So we had 10 per unit multiplied by our base value. We have 8,370 amps is what's flowing to the fault from the generator. So coming over here, figure out what the CTs are seeing. What's coming into our zone is 8,370 amps. We divide by CT ratio, which is 1,000 to 5, which is just 200. So one side of one CT is going to see 41.85 amps flowing through. The other CT will see 0 amps flowing out because we're not connected to the grid yet. And then what's our difference was I in minus I out. Either way, it's going to be 41.85 amps, which is much higher than our pickup of 0.5 amps. So this is a pretty easy decision. So the relay will trip offline. So you can see again, differential protection. Anytime we have a fault internal to our zone, that's a telltale sign, high current, that current going through an operating coil is going to be very strong, much greater than the pickup. So we're going to immediately trip offline and save the generator from any damage from the high amount of current. Okay. So that's for our exercise. So now let's start talking about kind of how to set up the 3 differential zones for a unit connected transformer. All right, so this is now we're in the more complicated version. So remember, for any bulk electric generation station, it's going to be a unit connected generator. So you're going to have your GSU right here. And then you're going to have your actual generator. So the first step is let's do our most internal differential zone, which is the 87G. This is right outside. So this covers the generator only. Generator only. And where are the boundaries, which is the CT? Well, if we only want the generator terminal, we're gonna have to put a CT set on the positive terminals of the generator. And then we're going to put another CT set on the negative terminal generator. Okay. And so coming over here, this is a positive wire coming out. This is a negative wire coming in. So we could just wrap a CT around it. And so we have our 87 right here. And you can see we have the CTs connected right here. And this creates our zone of protection like so. Okay. So that's for the innermost 87G. We could go and start talking about the second layer, which is our 87TG, or transformer and generator combination. So here, where this covers both the generator and the GSU transformer. So where the CT boundaries? Well, because they're coming in generators, one boundary will be the negative. So that's one boundary, negative terminal of the generator. So here we can see, here's an A7TG. We can see we're connected all the way to right here. Okay. Notice that this is a completely separate CT from the other one, the 87G itself, right? Because remember, one of the rules is for any differential zone, we want to have a specific CT for that one specific relay. We don't want to share CTs with other relays on a differential zone. Okay, so that covers the negative terminal generator. The other side we're going to have is the high side of the GSU. GSU transformer. So this is where the current's expected to go out on the system. So we need to make sure we could cover this and see all the current flowing out of the GSU onto the power grid. Now we would be done, except if you notice this node in the middle, there's 3 lines coming out. There's one line going this way, one line going this way, and then current going in. So more than likely, current's going to come from the generator. Some of it's going to go out to the main system, but some of it is going to come down into the unit auxiliary transformer. So we can't really ignore that. We should put another CT right here to then find that the current coming out that terminal. So you can see here, this is kind of unique in this. This is a 3-terminal differential zone. So there's 3 lines coming out, not just 2, which is what you've seen before. So again, let's wrap a third CT right here. This is going to be on the 13.8 kV side of the unit auxiliary transformer, UAT. Okay. So again, this is another big loop. And this one, as you see, also protects the generator. So right now the generator has 2 differential relays on top of each other, which is expected because, again, the generator is by far the most expensive device on the power system. So we need to make sure we protect it adequately. Okay. Third differential differential relay you'll see in the unit connected generator is the unit auxiliary transformer relay. So you have an 87 UAT. This will cover the auxiliary transformer. I think I misspelled this. I think this is a auxiliary. Okay. So cover auxiliary transformer. And again, what are the inputs and outputs of that? Well, you see here's the 87 AT. So, and again, transformer is pretty easy. You always got to wrap the low side. You always got to wrap the high side as well. Again, notice that this differential is different from the other notice this CT is different from the previous CT because we don't want to use one CT for 2 differential zones. We want to have 1-to-1, one CT for 1 differential zone. We have a second differential zone. We purchase a second CT. Okay. So one side is going to be the 13.8 kV high side of the unit auxiliary transformer. And the other side will be the low voltage side, which is a 14.16 kV. This is your low voltage side, low side of the unit auxiliary transformer. This is, again, your traditional 2-terminal, current going in has equal current going out with the turns ratio taken into account. Anything that doesn't have that balance, there's typically a fault inside. Okay, so that's another layer to your unit auxiliary transformer because you don't want to lose that. Now, all that differential packaged together gives you a pretty comprehensive plan for protecting the generator, even with multiple layers of differential. But like any protection plan, you want to diversify. And one way we could diversify is using something besides the 87 differential, because there's a chance, we never know, that every 87 relay could just not work. We had some manufacturer issue, or just our philosophy with 87 didn't work out too well. So a good backup is having a different type of relay help us. In this case, I want to use a 21 phase distance relay. So what we can do is we can have a relay at the end behind all their equipment, and let's have this relay look out from the edge of the generator, through the generator, through the bus, all the way out to right here at the end of the transformer, to about right this border. Okay, let's call this a zone 1. Because you remember, different step to a phase 21 distance relay has those, is an impedance relay that has the different zones. So let's have a zone 1 looking out into the system with a limit where we want our Z1 to be the impedance of the generator right here, plus the impedance of the transformer X of T, where this is our GSU. Okay. That way, if there's ever a fault within the transformer or the generator, our 21 relay should pick it up in case all of our differential stuff zones fail. Okay, there should be no delay for this 21 relay, but we should also make sure the 87 will trip first. Okay, remember, a backup protection should be slower than your primary protection. Primary protection is a 87 relay, 21 is a backup. Now, the 87 relay mechanically should act faster than the 21 relay by design. But if you're not sure, it might be okay to put like a 10 or 20 millisecond delay in the 21 relay just to make sure that your 87 will operate. The one place I could think that this could happen is if you have mechanical relays on your differential, but then your 21 relay is a microprocessor based one, which is a little bit faster. So if you're mixing mechanical microprocessor, you might want to put a small delay in the microprocessor to slow down to the speeds that the mechanical ones operate. Okay, so that pretty much covers the current protection for the actual transformer. Is 87 differentials all over the place with a phase 21 distance looking out as a backup. So I think we'll call it here for today. We're going to come back next time. We're going to talk about all the other type of protection we need for the generator that's outside of just, fault current is bad and we need to disconnect the system. So thank you for showing up and listening. I guess we'll have a good day and we'll catch you next time. So see you later.